Hi, everyone. So in the previous videos, we discussed what it meant for a function to be one-to-one and onto, and that led to the idea of an isomorphism between two vector spaces. Essentially, a finite dimensional vector space is essentially like one of the Rn spaces. So there's an idea that if we have a two-dimensional vector space, it's just like a plane in almost every way. If you have a three-dimensional vector space, it's in every way like three space. So we know that we have linear transformations that go between these generic vector spaces. We also know that we can have, if we ever have a linear transformation between our normal Rn spaces, there's a standard matrix for it. So we want to connect those last two ideas together, that for every linear transformation between two generic vector spaces, there's an associated matrix that goes with it. This is called the matrix of the linear transformation relative to the bases for the spaces. So previously, I've already shown you that a linear transformation can be completely defined by its effect on a basis. We did that last time with one-to-one and onto functions. It's entirely and totally controlled by how it's affected by how the linear transformation acts on the basis. We use this idea in order to find the standard matrix between Rn spaces. We're just going to repeat that process. In fact, a lot of the ideas are very similar to what you saw when I first introduced to you the change of basis matrix. So suppose that we have a linear transformation between two finite dimensional vector spaces, V and W. Let B and C be bases for the separate vector spaces. The number of vectors in here could be whatever. We don't really care. They could be the same or not. Now, for every vector V in the vector space V, just expand V in terms of the basis vectors found in B. So then let's say that B has n vectors. So then V is some linear combinations of the vectors in B. Next, go ahead and take the transformation of both sides. Remember, the linear transformation will distribute through vector addition and scalar multiplication. Next, go ahead and find out what the corresponding coordinates relative to C for these vectors, because whenever you take T of any vector, it's a vector in W and it has coordinates relative to the basis C for W. But notice that the right-hand side, that can be written as a matrix multiplication. It's the matrix formed whose columns are the coordinates relative to the C of the transform applied to the basis vectors. So there's n of those vectors. And you're multiplying it on the left to the vector, which is the vector B relative to the basis B. Because the vector V relative to B are literally the scalars C1, C2 up to Cn. So because of that, we get this idea that if you ever have two finite dimensional vector spaces and a basis B and C respectively for those vector spaces, where B can be written as it's a set of V1, V2 up to Vn. If T is any linear transformation from V to W, then there is a M by N, M, because C has, I suppose, M vectors in it, but we know that B has N vectors in it, so it has N columns. We denote this as T with a box around it, where we have the notation in the lower right-hand corner of B goes to C. You say that is the matrix of T with respect to the basis B and C. If we keep saying that, though, it's going to be hard to follow. So I normally just say the matrix of T from B going to C. It makes it a little easier to say. So this matrix of T going from basis B to basis C is a matrix that's M by N, whose columns are the coordinates of the vectors relative to the basis C of T applied to the basis of B. This happens to be, in fact, the only matrix that if you ever multiply a matrix by the vector, which is the vector relative to B, it is exactly the same thing as the transformation applied to V, but that thing in terms of C. In notation, then, we have that the matrix relative to C, the matrix of T from B to C, if you pre-multiply it on the left to the vector B relative V relative to B, you get the vector T of V relative to C. That's what the very bottom equation says. That's what this one here says right here. Notice that the notation kind of suggestive. Do you see how B and B, it gets sent to C? So the result is the result of T applied to V, but its coordinates are in terms of the basis C. You obviously are going to need many examples to feel comfortable with what I just said. It is not difficult though. I'm going to have a whole separate slide, a whole separate video just for about 4 or 5 examples. So let's just start off with an easy one. So suppose T and V are the same space, and B and C are the same basis. So there's really only one basis. In that case, we don't write the matrix of T relative to B, because that's just hard to say. We just say the matrix of T relative to B. So there's only one subscript. In that notation, we have that if you want to take T and apply it to V, and you want to know what its coordinates are relative to B, instead take this matrix and multiply to this column vector, and that would be the answer. Now, as a picture, so that you understand what my examples are trying to say. If you start with the vector space V, there's a vector V in it. You could then take T of it to now get a vector in V again, because T and V are the same thing. T and W are the same thing. Then from here, you could then find its coordinates relative to B. And when you do that, you're actually applying another linear transform. The linear transform is the transform that assigns a vector to its coordinates relative to B. We know the mapping of coordinates relative to B is 1 to 1. And since V and Rn have to have the same dimension, R would be not only 1 to 1, it'd have to be onto also by the theorems you learned last time. So then the R is actually an isomorphism. In fact, that's the very first isomorphism you ever actually learned. It's just the coordinate linear transformation. We used it many times to prove lots of stuff. So remember that in an isomorphism, all you're doing is changing the name of the vector. You're not actually changing the operations. You might change the way they are represented, but you're not actually changing the vector. You're just giving it a different name. Now, if this is true, if this is one way to do the mapping, you could also instead find V's coordinates relative to B first, and then take that vector and pre-multiply it on the left with the matrix of T relative to B. When you do so, you have to get the same thing. This is what's called a commutative diagram. It means that the order of the operations of these two things doesn't matter. You can do either way, you'll get the same answer. You'll still get the same representation. Remember, it's a representation of the result. And there's many ways to do so, depending upon the basis we use for the image space. So it says then that R composed with T is the same as T of A composed with R. So the R operation commutes with these two other operations, these two other linear transformations. So we can use the coordinate transformation anywhere we wish in this process. All right, let's just go and do some examples. Let's look at the linear transformation going from R3 to R2. Defined as I have it here. The basis for R3 will be E1, E2, E3. The order matters. The basis for R2 will be E2, E1. So notice that B is just the standard normal everyday basis. C, though, is the standard basis where I reverse the order. Again, the order does matter. The order does matter. So let's find the matrix of T relative to B and C. To do so, the first thing you have to do is you have to apply the transformation to every vector in B. So I did that for you here. Just cranked it out. The next thing to do is to find the coordinates of each of those mappings relative to the basis C. So T of E1 is the vector 1, 1. But that is E2 plus E1. T of E2 was negative 1, 1. But that is E2 minus E1. And T of E3 is 0, 2. And that is 2 times E2 plus 0, E1. The order here matters because we have to get coordinates relative to the basis, and the order of the vectors in the basis matters. So the coordinates then are the coordinates of E of T1 relative to C is the vector 1, 1. It's the scalars used in the linear combination. T of E2 relative to C is 1, negative 1. Again, that's the scalars in order used in the linear combination. T of E3 relative to C is 2, 0. Again, that's the order of the scalars written in the linear combination. And the order, of course, depends upon the order of the vectors in the basis for C. That means I can find the matrix of T relative to B to C. It's just the matrix of the columns of the vectors that is found. So the matrix is 1, 1, 2, 1, negative 1, 0. Let's make sure you understand then what that computation means. I gave you the transformation, and I also gave you the matrix of T from B to C. So look at the vector V, remember the mappings. I'm gonna find T of V first. That gives me this. And then I'll write that down relative to the vector, relative to the basis C. So that then is T of V relative to C, 7, 1. So if I do it in the other order, where I find the coordinates and then do it by matrix multiplication, I better get the same vector. So here's V again. That's the vector relative to B, the basis. Remember, the basis for B is E1, E2, E3, so then it's the exact same vector. So then T, standard matrix of, well, the matrix of T from B to C, pre-multiplied on the left by the vector. Well, no, actually, so if you multiply that by the vector V relative to B, you then have to get, by the matrix multiplication, you get the same vector, you get 7, 1. Remember now, this thing here is just the representation of that image. So if you want to know what the vector is, you have to go back and notice here are the scalars so that you can figure out what the original vector was. All right, that's one. Let's just look at what I just did again. There might be some confusion because there is a standard matrix. When you go from Rn to Rm, there's a standard matrix. That's not the same as this. They're related, but it's not the same as the standard matrix of T when you have Rn to Rm, and the matrix of T relative to a basis B and a basis C are not usually equal to the same. They're not usually equal to each other. As you can tell here, they're not. I wrote down the standard matrix for you. That's just the standard matrix of T is the matrix 1, negative 1, 0, 1, 1, 2. But if B and C are the standard basis, then actually they are. So if all the bases used from Rn to Rm, if all the bases are the standard basis and the order they're supposed to be in, then the matrix of the transformation from basis B to basis C is the same as the standard matrix. It's the same thing. But if they're not the same, if one of the bases is the standard basics, but with things flipped around, then the standard matrix and the matrix of the transformation is almost the same. It's just that rows are swapped or columns are swapped. Remember, when I found the matrix of the transformation from B to C, C's vectors were E2, E1. They were reversed. Because of that, if I wanted to, I could have just gone and taken the standard matrix of T and I just flipped the columns. I just reversed the column. I reversed the rows and I would have got my matrix of the transformation from B to C. Again, notice if I just take the standard matrix and if I just flip these two rows, you get the matrix here. So as long as the bases are standard bases and don't the normal order, then the standard matrix and the matrix of the transformation relative to those bases are the same thing. I believe that's enough for that introductory video.